Okay, so today I just want to quickly just start with a couple slides from the notes that I have on linked lists as well for you grade 12s. Just as a bit of a review from what I talked about yesterday. Okay, so the term ADT stands for Advanced Data Type. It is a generic term to describe a bunch of data types that you can program with that are beyond the primitive data types like integers and things like that. So with lists of things, we had the ability to use arrays, but now we want to go beyond just its limitations. So arrays are static objects that cannot change size. A more dynamic object that could grow or shrink, would be more useful. And the first one we're going to look at is known as the linked list. Okay, and we started this yesterday. It is a collection of data items that are lined up, where each item maintains a, quote, pointer, which, by the way, is a term that in Java really isn't necessarily used that much, the term pointer. But in other languages, like, for example, C++, this is an actual type, a pointer type. Again, this may be something you'll encounter if you research code beyond what I teach in the classroom. It's really kind of, again, just that idea of a reference, one thing referencing another. Okay, so here's again the diagram where you can see the linked list in action, where one item connects to the next, and eventually the list has to end, unless it comes back around to the beginning again, which is known as a circular list. Okay, the term that's used for each item in the list generally is called a node object, which contains the item, which could be an integer, it could be anything, and a pointer to the next node in the list. Okay, so here I have an example of how you could insert a new item quite easily by just redirecting the pointer, okay, to a new node and then connecting it into the list. Whereas with arrays, this would be impossible. You wouldn't be able to do that easily with arrays. To delete an item from the list, you again redirect a pointer around the one you're deleting and then sever that one from the list. Okay? So it's much easier to add and delete to list items than it is to array items. So again, C++ has things called pointer objects. Java technically does not have type pointer, but it has what's called a self-referencing class, which is what we designed yesterday. Okay? In my notes is another example of a node object. It's a simpler one than the one we did yesterday. But I just wanted to quickly catch up on that from yesterday as well. We did this diagram yesterday of nodes, and we talked about references. Okay? We talked about how references could even apply to things like classes. I showed you how that kind of fits out, and then I compared arrays and its limitations to something else, which was the linked list object, okay? Where we could, as you just saw in the animation, connect or link things into the list, okay? And how it was self-referencing. And that's where we got to yesterday when we wrote this code, okay? So the node object, as you can see, contains data, and it contains a reference to the next node and a reference to the previous node. This is known as a doubly linked list because it links both forward and backwards in the list. Okay, so it's a little more advanced than a singular linked list. We had a constructor. We actually had 4 constructors that we wrote that basically just assign those 3 properties their values depending on the way you're constructing it. Some of those values could easily just be null. Then we wrote a couple of useful methods that are available in most classes. The toString method, the equals method, okay? These are methods that are overriding, okay? Methods built into most Java objects that derive from the object class in Java, okay? We also wrote methods destroy and clone that might be useful in the future to do these things. These are just kind of like standard little methods that you may want to put in most classes you write. Things like, can I compare this class to another one? Can I make a clone of this class? Can I destroy this class when necessary? These are just sort of things you'd want to do generally. So today we're going to now add to this project another new class. So you want to go new Java class, and you want to call it linked list. The spelling of that is both L's should be capitalized, right? Linked and list, because it's really 2 words. So here you can see I've spelled it linked, capital L, list, capital L. and add that class to your project. Okay. So class linked list. Now, this linked list will use the other class we just wrote, the node class. But the node class is a generic class. So our linked list class must also be a generic class. So just like we did with the node class, up at the top in the class signature, in other words, the line that defines the class, we're going to add that angle bracket T. Okay, and again, it doesn't have to be T, but for the purposes of this, we're going to use T. Okay? So we've added this up here to indicate that it's a template for generics, which essentially means it will be whatever data type we need it to be. Okay? As long as it's a class, we'll be able to link them together using the node class that we've already built. So it'll be a connection of that. Now, think about the way this linked list will be looking once it's built. It'll look something like this. It'll be a node connected to another node, connected to another node, connected to another node, etc. We also have this as a doubly linked list, so it will not only be linking forwards, but it'll also be linking backwards. But at one point of the list, the beginning of it, this link will link to null. It'll be connected to nothing. And at the end of the list, this link will be connected to null. But that will be our list, and it could be very, very long or very, very short. But in order to use this linked list, we need a way to get inside the connection. How do we start this? Now, again, you can compare that to arrays. Arrays, you know, always start at index 0. That's where you start looking through an array, is at index 0. But there are no indexes in a linked list unless we make indexes for it. It doesn't automatically give each node a number. So we need a way to enter into this list. And most likely you would think that you could start at the beginning. And you're right. The beginning of the list is a way to access or get into the list. But at the same time, we could also go into the back of the list. Think of this again maybe like a two-lane highway where you first enter the highway and start traveling along, or we could enter on this way, and because it's linking backwards, we could go either direction. So the name given to enter these traditionally is called the head of the list and the tail of the list, which kind of makes sense, right? If you think of it as a long chain like a snake, that's the head and this is the tail. Okay? We need references. We need connections to get in to the head and the tail of this list. As well, if we want it to work kind of like an array, it's probably a good idea if we keep some sort of a count going of how many spots are in this thing. Okay? These would be 3 useful things to know about now that we're dealing with the list as a whole. Is the head, the tail, and the count. And that's exactly what we're going to do now, is we're going to write those. We're going to write them as properties. They will be private properties. Private, oh, that's not private. Private. Okay, so for example, to keep a track of the count, we're just going to use an integer. Okay, and we'll call it length. So that will keep track of the number of nodes in our list, is the length. We will also keep track of this, private node head and private node tail. Now, here's where it gets a little bit weird. Okay? These two so-called nodes are not actually going to be nodes. These won't be built into nodes. These will just be references. Okay? In other words, they will just be connected to real nodes, which we will build inside the inside the list, pardon me. So these will just be references. Notice we don't say head equals new node, tail equals new node. We also don't give length a value because there is no length to this thing yet. It has no size right now. Okay. Now we need a constructor for our class. So public linked list. We'll make a default constructor for our linked list. Now, all the constructor will do is it will set these to be their values. So length will be equal to 0, head will be equal to null because it has no size, tail will be equal to null. As well, before we write that, if we think ahead a little bit, just like we did in the node class, when we made the node class, we made all these useful methods for it, things it could do, including a bunch here at the end. Remember I said these methods are going to be kind of useful in any class you write from now on. Not necessarily need to add them all. But when we think of the linked list, this might be a useful method to write again, how to turn the entire linked list into a string for things like spitting it out so we can see everything in the linked list. Equals? Maybe. I don't know if we'll need to check to see if one linked list equals another. Clone? I don't know if we need to do that either. But I think we will need to do this sometimes. We'll need to wipe out the whole list, destroy it all. Okay. Well, let's do that. Let's destroy the list right now. So let's take that method over to here and write it. Public void destroy. Oops. And really all it's going to do is it's going to say length equals 0 and head equals tail equals null. We'll set all those to null. And the reason why I thought I'd throw that in now is to just destroy the list this way, is that's what the constructor does too. The constructor essentially does the exact same code. So why waste a line of code? Let's just call destroy right here. Now here comes another interesting little point here. You're going to notice a light bulb pop up here in NetBeans, and it's not an error, it's a warning. It's saying, hey, you're calling a method right when you construct it. I think I have some ideas what you should probably do with that. And some of the suggestions it says is make the class final. Well, that wouldn't, we aren't going to like not change this class. So making it final is not a good idea. And a few of the other ones, but the one that I would actually suggest you might think about doing is it suggests that we put the word final into the method name of destroy. And without going into a lot of detail, I think that kind of makes sense to do. Think about it. Destroying a list is kind of the final thing you'll do with the list. Before you rebuild it into a new list, you will say, you know what? This is kind of a final thing, right? That's kind of like when you delete a file, it says, are you sure you want to delete this file? Of course it's kind of a very final thing. So that kind of is a good suggestion. It's saying that this method is kind of a finality thing happening there. Okay, again, I didn't want to get into too much detail on that, but okay, so here's what we got so far. We've got a linked list that you can build and destroy. That's it. But it has no content to it whatsoever. So before I go and give you a list of methods that I think we should write, why don't you tell me things that you think this linked list should be able to do? Like, what should this linked list be able to do? Okay, I'll give you the first one since you guys are quiet today. We need to add things to this list, right? Put things in it. What else? You guys are quiet today. Well, we need to delete things from the list. Okay, but when I say add things, I'm not being detailed enough. Add it where? It's a list, right? So I could add it, for example, at the beginning. Or maybe at the end of the list. And now we have names for that. What is the beginning? It's the head, right? And the end is the tail. But as well, maybe there might be times I might want to add it in the middle of the list. How could I do that? Well, it's possible. Okay. Delete things. Well, delete things would be essentially the exact same thing. I delete things from the beginning, the end, and the middle, which again is way more than an array can do. You can't do that with an array, or can you? Well, you can't delete things at all from an array. It's a locked in size, and you can't add things at all because it's locked in. But some things that arrays can do is we can get things. Get from an index, right? So if I say, give me what's at spot 5, in an array it'll tell you what's at spot 5. We don't have that ability yet in our linked list. We should write that. We should be able to do that. We can also change things in an array. Change an item at an index. So we could say, you know what? What's at spot 5? I now want it to be this. I don't want it to be what was there before. Okay? Or in other words, we could set an item at an index. Maybe that's a better word than change. And it is a better word. The words get and set are very common in Java code. What else could we make this list do? Let's go beyond what an array can do. Because now we're kind of just what an array can do. Get, set, delete things, add things. That's really not that much more than an array can do. What else could we do with this list thing? How about we could use something we've done already? How about we could sort it? How about we could search it? That'd be kind of cool if we could do that. If that was built right in, sorting and searching. How about saving? We've done a unit on files. We could save the list to a file. Maybe we could open from a file. That's cool. We already kind of have that ability. We already wrote code on that. Maybe we could connect our other units to our linked list here and make this giant thing that could do everything. Could kind of, as long as we have a group of data, it could just organize it all real nicely. This is what I'm saying. We could build these things into the class if we have time. So this is like our little possible to-do list here. So I'm just going to leave this as a sort of a comment here in our code. These are the things that we could start looking at. So let's do that. Let's get started on this. But before I do, is there anything that you guys think possibly could be added? I'm going to show you real quick. This was from last semester, a class that I worked with. Connor was in that class. And I presented the same thing to them back then. And this was their list. A constructor, yes. They came up with something that says save, open, compare, sort, search. They came up with this idea to turn the entire list into an array. So let me think about that for a sec. That might be cool. What if we could turn the entire linked list, because sometimes you might need it as an array. Maybe we could turn into an array. And maybe we could turn an array, go the other way, into this list. So arrays can be useful. Why don't we give this thing the ability to change itself into an array? Or change an array into the linked list if we need that. So maybe we could start off as an array and go, well, this array isn't useful anymore. Boom, now it's a linked list. So we could do stuff with the linked list and go, you know what, I actually need it back as an array. Boom, now it's an array again. So that might be cool if we could do that. So that's a long list of to-dos. Let's see how it goes. Okay, so we're going to start with the very first thing. We're going to do an insertion. So public, okay, void, insert, and we need some parameter for that. We're going to be inserting data into the list. The data is of type T, because we don't know what the data is yet. It could be anything. Okay, so we're going to be inserting data into this list. Okay, so now I want to just, and again, you guys don't have to code this. I'm going to go back to main, which we were at yesterday. And remember, in main yesterday we were testing nodes. So I'm not going to test nodes anymore. Nodes are taken care of by our linked list object. Linked, list, but it's a generic data type. So I'm going to give it a linked list of integers. I'm just going to call it list equals a new linked list of type integer. So this line of code will call the constructor we just wrote, this one right here. But it will change the generic data type T into a linked list of integers. And again, this can be whatever I want it to be. As long as this is a class, we're good. So it could be strings. It could be a class you make called like class enemies. If you were making a game and you were making a big giant list of enemies, you could do that, okay? So that becomes incredibly useful to you. So we'll do that. Now now that the list exists, I should be able to go list dot, and I can call the methods that are built into it. So as I said to you guys yesterday, some of these methods, like these wait methods, are part of something called threading, and they're not something we're going to need. Same with notify, and same with hash code. And get class is kind of a useless one as well. But as I said to you guys yesterday, some of them are built in, like toString is already built in, and equals is already built in. But these two we wrote. We wrote destroy, and we wrote insert. And notice what insert did now. When we wrote insert, we put a T there. But now it has changed into integer because we told it it's a linked list of integers. That's pretty cool that it does that for you. Okay? So if we wanted to, we could destroy the list, which is useless because the list is empty. But it's the insert that makes more sense to call here. We're going to maybe insert like a 10 into that list. But as I said before in the commentary, inserts really should be thought of a little bit more closely. Where are we inserting this? At the beginning, at the end, at the middle? Yeah, we got to pick one to start with. So let's do beginning. So let's rename this, not insert, because that's too simple. Insert head. Let's call it insert head, which will now crash this. So I'm going to get rid of that line for now. Okay? So we're going to insert this data to the head of the list. Okay, move that down. Okay, so let's think about what's going on here right now. A little quick diagram. We have just constructed this thing called list. It's a linked list. That's what it's called. It contains three properties. It contains a very simple integer called length, which is just an integer. And right now it holds the number 0 according to our constructor. Our constructor said set that to 0. It also contains a reference to the head and a reference to the tail of the list. And these two things right now are pointing to null. This is what exists in our linked list right now. Basically nothing. We've now passed it some data. Let's say we gave it the number 10 is sitting inside this parameter right here. What we want to have happen is we want to build a node, which is good. We've got constructors to do that. We want to put the 10 inside the node. This will be linked to null. This will be linked to null. And then this will now go to here, because that's now the head of the list. But because it's the very first one, this will also go to here. And that would essentially then connect it into the list. Okay? However, that will not be the case when we do it the second time. So the second time we insert into the list, now we'll have a 10 in here. This will be the head. This will be the tail. This will be null. This will be null. Our length, which will be sitting over here somewhere, will now be at 1 if we write the code to add that in there. But let's say we insert a 20 into the list this time. The same kind of code will happen. It'll say, okay, build me a new node, put the 20 in there, set this to null, set this to null. But now think about what has to happen. Now, the head will now go to here because that's inserting to the head. The tail, however, doesn't change. It would stay there. But in addition, I've got to make some more connections. This is now the front of the list, which means this thing has to point to that guy. And this one, the one going back, will now have to point to that guy. So there's some logic to deal with here. And it depends on whether I'm inserting a node for the very first time or not. So let's get to work. I just wanted to sort of throw that out there. Okay? So one thing that happens no matter what, no matter whether I'm inserting it for the first time or the second time, is I'm building a new node. So let's do that. Let's make a node called node equals a new node. And I have to also define t with it because it's passing along that data. And I'm also going to pass it data. Okay? And I believe I should put the t here too. Yeah. Okay? So that's what I do right there, is I say, okay, no matter what, build me a new node. And it passes the generic along with it. So in this case, I'm building a node with an integer inside of it. Okay? Because that gets passed here. So it says integer gets passed along. And it'll call the constructor in the node class that matches it. So in this case, I said, just give me the constructor with just data. Well, that's this one right here. So it would go like that, and then it calls, you know, it works. It's all laid out for us already. Okay, whoops. Okay, so that's the first thing, is I construct a node. But now I got to think about the logic here. If it's adding the node for the very first time, then I got some logic to deal with. But if it's every other time, I have different logic here. So this is a basic if statement, right? If it's the first time, else, if, else, right? Kind of a thing. So in order to think about the very first time I'm entering something, I'm going to write a little method below here that would be useful for doing with that. Basically, I'll know it's being added for the first time if the list is empty. So I'm going to write a little public, sure, let's make it public, Boolean method, it's going to be really simple, called isEmpty. Is this list empty? And it'll either return true or false. Okay, it'll just say, yeah, it's empty, or no, it's not. Well, this is actually really easy code to write. How can you tell if a list is empty? Well, it's simple. If the length equals 0, return true. Otherwise, return false. It's very simple. I can just use that little variable I have called length, and it'll tell me. If the length is 0, it's empty. Otherwise, it's not empty. The code we're going to write, by the way, is not that long, most of these methods. They're very, very short. Okay, now, for those of you who want to jump, I like this code for isEmpty, but you can actually turn this into one line of code. And I'm just going to show you what it would look like. If you want, you could just do this. Okay, so I just want to show you guys this. And do you understand how that works if I just do that line? Who can explain that this one line of code is equivalent to that if statement? Okay, think about what's going on here. This code right here is exactly the same as I placed in the if statement. How do if statements work? If statements work on a true-false test. That's the test. So that same test will give you true or false. So in other words, it will either return true or false. So if you can grasp that, if that kind of makes sense to you, then by all means, turn that method into a one-line method. I'd be fine with that. However, if this is still kind of confusing, then I would recommend just leaving the longer version in like that, because it might make a little more sense to you. Okay, I'm going to go with the simplified version. Why not? Okay, so now we come back here to insert head. Now we can do that test. We can say, well, if is empty, if it's empty, then I got to do one thing. And if it's not empty, then I'll do a different thing. Okay? So now the insert head method will kind of make a little more sense. Okay? Now, before we go and write a whole bunch of logic, let's jump ahead just a little bit here. I'm going to copy this whole method insert head at this point and paste it just below and switch it from insert head to the other one, which is insert tail. So now, let me just zoom back. I've got two basically the same methods here, insert head and insert tail. And they're kind of, at this point, looking the same. But they're really not going to be the same. There's going to be different logic in each one. But think about this scenario right here in both cases. When it's empty, insert head and insert tail will both do the exact same thing. These two things will be equal, right? When I'm adding it for the first time, whether I'm inserting it to the front or the back, it's the first one. So no matter what, this will be the same. So why not take advantage of that and optimize our code a little bit? And the way I'm going to optimize it is now, let's go back to insert head for a sec. When I insert it to an empty list, why don't I just call insert tail like that? Which means I can actually get rid of some of these brackets just to free up some space in my code here. So I'm just going to do that. When it's empty, I'll just send it down here and let it do the work. And I'll deal with that later. When it's empty, I'll just insert it to the tail, because it's the same thing. Okay. But otherwise, I got a little bit more work to do. So here's now the scenario that I have to deal with. I'm going to forget about adding the very first one. So we can imagine now we're inserting to a list of at least one node. At least one. It could be 100 nodes. But we want to insert, so let's say we have this list that looks like this at this point. Let's say it's 2 nodes, like that. Linking forwards and backwards like that. This is the head, this is the tail. We are going to insert data into the front of this list. So I don't care about what's going on in the tail. All I care about is what's going on up here. So here's what we have so far. Let's say we're inserting the data 10 into this list. So it will construct a new node. It'll put the 10 in there, and this will be null and this will be null. This is right now called node. That's what it's called. Okay? Here's what we need to do. We need to attach this node to what is right now the head of the list. We need to make a connection there. We also need to attach what is currently the head to this thing called node. Notice how that will link it in. And then one other thing we need to do is we need to tell this thing that's currently pointing to head to say, now make this the head. So what I've drawn them in red is those are the 3 things that need to happen. Essentially 3 lines of code. Change this, change this, change this, and one more thing. That little variable we have called length, it has to go up by 1. Okay? It has to add 1 to itself. Whatever it is now, it goes up by 1. So we really have 4 lines of code to deal with here. But we have to find a way to actually execute those 4 lines. Right? Let's think about how this will work. Maybe we'll start with this one. How do I change this connection right here to actually be what I said? Well, I need to refer to this. Well, this thing is called node. That's its reference. Node, but what's this inside of node? How would we call that? That's node dot next. So if I say node dot next, I'm talking about that connection. And what do I want it to connect to? I want to connect to that thing. What is that thing called right now? It's called the head, right? That's what it's called. So if I say node.next equals head, that should do what I just said to do. It should make this connect to that. So that was a way you could reference it. Now, how could I adjust this line? Well, I need a way to refer to this thing. What is this thing? Well, we'll start with the reference head. I could say head. So now it knows I'm talking about this thing. Dot, what's this thing in head? It's going the other way. It's the head dot previous. So now I'm talking about this connection. And what do I want it to go to? What do I want to set it to? Well, I want to set it to this thing. And what's this thing's reference? Node. So I could say equals node. and that will make this connection happen. And then finally, what's that? How do I shift this back? Well, I then can just say head equals node. And it'll shift this now to that reference. So here's again that important idea of referencing. Knowing what everything is essentially called will be the way to make that happen. So I know I got a lot of mess up there, but I'm actually going to type it from there. Node.next equals head. Head.previous, then I'll clear the screen. Equals node. And head equals node. Okay, so now I'll clear up the screen so you guys can see the code that I had up there. Okay? Now, here's a question, if you guys have been paying attention. Does the order of these lines of code matter? It does. Especially this one. Because think about it. Let's say I put that line first. Okay? So let me just quickly draw this. Okay, so let's say that line was first. This is currently head. We've just built a new node right here called node. Okay? So if I said head equals node right there, it would shift that first. Then if I said node.next equals head, what would it do? It would reference itself right there. And then if I said head.previous, that's this one, equals node, it would reference itself. You're essentially now cutting off the rest of the list is being cut away from the head at that point. So yeah, the order does matter. If you screwed that up, it could essentially screw up the... by the way, there's one more line to write. For those of you who might have forgotten it, we also have to take length and add 1 to it. So length plus plus. And that's it. That's insert head. That's how we insert a node to the head of this list. But it also relies on insert tail, which we haven't finished. So we gotta, before we go and do anything like try and test this, let's quickly before the bell try and write insert tail. Because the reality is it's actually mostly the same. Except when it's empty. When it's empty, the tail equals the node, and the head equals the node. That's how we add it to an empty list. And remember, that happens whether it's insert head or insert tail. I just stick the head and the tail to the node. It's really simple. To insert it to the tail, let's see if you guys can grasp this. This is going to be easy as well, if you think about the way the references work. So here's this kind of big test. So now we can assume we have a big list. So let's assume this is the big list going on. That's null, that's the head, that's the tail. And here's what we just did. We created a new node. Let's say we stuck a 10 in it. This is null, this is null, this is called node. Okay? We are not, it's not empty, so we're calling it to insert it to the end here. Okay? What do we have to do? I'll write them in red. One thing is we got to connect this to this. We got to connect that one back to that one. And we've got to take this and point it to there. In other words, that goes away. And the length will go up by 1. So it's basically the same code as the other one, but you need to know how to reference it properly. So can any of you tell me the 3 lines of code to make that happen? Close, but not tail.previous. Tail.next. Tail.previous is this one. Yeah? So tail.next equals node. That'll do that one. So I'll put a check mark. Stephen got that one right. What else? Yeah. What's the next one? Correct. And then lastly? Correct. You got it. And it's all based on the fact that you know how to reference that stuff. Okay? So let's write that. So else tail.next equals node, and node dot previous equals tail, and tail equals node. And lastly, don't forget, length plus plus. And that should complete insert tail. So we now have the ability to insert nodes to either the front or the back of this list. You can do either, front or back. Okay, we got a couple minutes. I'd like to actually test this, but there's no way to see if it's working unless we write one more method at this point. We need to write one more just to test this. So let's go down and write one more method. So in order to spit out this list so we can see if it's working, let's override the public string toString method. That was the same way we did it in the node class. Okay. Now, it's possible that the linked list is empty. So if is empty, let's just return some words, empty list. So we'll just return that if it's empty. That's simple. But if it's not empty, if it's not an empty list, okay, let's start building up a string of text. So we'll just use the word list. List equals, we'll fill it up, and at the end we'll return that text. Okay, so here's what I'm saying. We are now going to turn the entire linked list into a string. This is so we can test it. We can spit it out. If the list is empty, we'll just send back the words, this is an empty list. But if the list is not empty, we're going to build up a string of text. Okay, what you're going to learn real quick right now, and we'll go over this in more detail tomorrow, is how to what's called travel or traverse a linked list. Here's how it's going to go. And again, I'm going to go into more detail tomorrow. So I'm just going to basically give you the code today and explain it tomorrow. We make a node called current equal to the head. While current is not equal to null, okay, we will say text, that's our text variable, equals text, or text plus equals, our current, which is a node, which can turn itself into a string, plus some sort of separator, we'll just put a comma there, right, some sort of a comma. And then current equals current dot next. And again, I will go over the big details on this tomorrow. But that is our toString method completed now. Now again, I'm trying to watch the bell here and the time we have left in the period. So I'm just going to quickly now demonstrate if this is actually working or if we have a logic bug to deal with. So I can see some of you guys are typing, so I'm just going to ask you to lift your fingers for a second, take a break. I promise I'll put it back there. Here now will be the test. I'll say list dot insert head, and I'll just put, I'll put a 10 in there. So 10 should be at the head of the list at this point. I'll call it again, and I'll put a 5. And the reason I'm putting a 5 is because 5 should go before 10. Then I'll call it again, but this time I'm going to insert to the tail a 20. So in theory, it should go 5, 10, 20, right? Because I put something at the front, then something else at the front, so it would have gone in front of the 10, and then a 20 at the back. I can test this by outputting my list. Because list can turn itself into a string, this should hopefully go 5, 10, 20. Let's see what happens. It says it's an empty list. So we got a bug. Okay? So somehow it thinks that this is an empty list. And the only reason it would return an empty list is if the length is 0. So that's something we're going to debug tomorrow.